Hi there. In this video, we'll take a look at a classic topic in calculus called related rates. This video is part of a sequence of lessons in which we explore the question, what can we do with derivatives? Okay, and so the general idea here is that if we have two quantities of interest and some idea of how they're connected, we can look at their rates of change and we can determine using calculus how the rates of change are connected. Okay? This example is taken from page 247 of your text, and in it we're looking at a police cruiser which is approaching a right-angled intersection from the north. We're chasing a speeding car, exciting drama, which has already turned the corner and is now moving east. When the cruiser is this far north of the intersection, the speeding car is this far to the east, and the police are able to determine with radar that the distance between their car and the car that's speeding away is increasing at 20 miles per hour. And as you can imagine, the police are probably going to stop and really quickly do a calculus problem to see how fast the car is moving, knowing that their car is moving 60 miles per hour at that instant, and they would like to know how fast the car is moving away. All right, so let's see if we can help the police out with this calculus problem. Let's go. Before we get started, this is really 1 part calculus and 9 parts problem solving. So let's just kind of take a roadmap, big picture view of what needs to happen. As always, we need to make a heavy investment in attempting to make sense of the problem, knowing that drawings are helpful. If you can sort of like tell your own story in your own words, you probably have a good understanding, so that's something worth trying to do. Deciding what's important, what's not, what information you have, what are you supposed to find. Okay, and ultimately, we'll use variables to represent the quantities of interest. We'll write down an equation that relates those variables using our knowledge of math. And then we'll come up with an equation using calculus that relates their rates of change by taking a derivative. Ultimately, we'll then solve the problem, state the solution, and interpret our answer back in the original context. All right, so to that end, this is a very text-heavy problem. I've just split it up into some bullet points here. So let's try to visualize what's happening. The police cruiser is approaching a right-angled intersection, bam, from the north. So we're coming from this direction towards the intersection. And we're chasing a speeding car that has already turned the corner, zoom, and is headed east. So that car is moving in this direction. Okay? And to really help you understand, let's actually visualize this dynamically so we can see things in motion. Okay, so the cop car is headed towards the intersection, like that. The robbers are headed away from the intersection like that. But the real action is to visualize these things simultaneously, and the chase is on. Boom. Okay, so that's what's going on with the scenario. Okie doke. Let's see what information is available to us. Well, when the cruiser is a certain distance north and the speeding car is a certain distance east, we have some information about that. And knowing how fast the police car is moving, we want the speed of the other car. Okay? In other words, if this guy is going 60 miles per hour, are we able to determine how fast this guy is going? Well, let's see if we can learn the answer. Okay, and in terms of the information we're given, we know that the distance between the cars is increasing at 20 miles per hour. So this speed at which that's changing is 20 miles per hour. Again, this is helpful to have a visual for this, so let me pop over to this guy. All right, and we can observe the chase again right there. Oops. Okay, and let me just bring my labels out. Bing, bang, boom. Okay, so what's going on here is we have that the police car is a certain distance from the intersection. Can I back this up? We have that the the robbers are a certain distance from the intersection. And we have that the distance between the two cars is increasing at a particular rate. Okay, so that's what's going on. Okay, and let's see if we can put this information into a table. Okay, to help sort of organize the info, let's make a table. All right, so I've chosen as variables here, and did I write this down somewhere, I believe? Let me scoot this up. Okay, so quantities that are of interest, we have this distance is changing as the car moves down. This distance right here is changing. Let's call that distance y since it's vertical. This distance as the speeding car moves away, this horizontal distance is changing. Horizontal, I like x. And I'm going to use d for derivative, so normally I would use d for distance, but that letter is taken. I'm just going to make up the letter w to represent the distance between them. All right, so just to be clear, y will be the distance from the cop car to the intersection. X will be the distance from the intersection to the robbers. And w will be the distance between the two vehicles. All right, so we've got a clear definition of our variables, and that was something that we knew was important to do. Using general problem solving skills, we know that that is important, so we've done that. Good. Next, let's now use those symbols and try to put these numbers in the right places. Okay, so here goes. It says when the cruiser is this far north of the intersection, stop right there. That's telling me that this distance right here is 6/10 of a mile at an important moment. So that would represent the value of y at that instant. Okay, keep reading. The speeding car is this distance to the east. Stop and interpret. That's telling me that this distance right here is at that moment 8/10 of a mile. So that would represent the value of x at that particular moment. And you may notice that we are not told what the value of w is, but I bet we can find out using our math skills. We'll do that in a moment. Okay, but let's keep reading. Okay, let me just clean this area up for you. All right, as we continue to read, it says, at that moment, the police determined with radar that the distance between them and the car is increasing at 20 miles per hour. In other words, the rate of change of this quantity, which is, using the Leibniz symbol, dw dt, the rate at which w is changing with respect to the time variable, okay, is 20 miles per hour. So we'll write the rate of change of w is 20. Okay. Next, what else do we have up here? The cruiser, the police cruiser, is moving at 60 miles per hour. Okay. At the instant of measurement, and we want the speed of the car. Now, before I go ahead and record that information, it's important to stop and really think about some facts here about calculus. So, what do we know about y? Well, we're told y is 6/10 at a particular moment. What is y about to be? Well, it's about to be closer to the intersection. 5/10, 4/10, 3/10, 2/10, 1/10, no tenths, and now we're at the intersection. So in particular, y, the quantity that y represents is decreasing over time. And what do we know about derivatives for functions that are decreasing? Well, the derivative must be negative. All right, what about x, though? Let's go back and look. X, we're told, is 8/10 at a particular moment, so 0.8. And this car moving in this direction will soon be 9/10 of a mile, and then a full mile, and then more than a mile. And so what's going on there is we see that x is increasing, and therefore its derivative is a positive quantity. Okay, and the summary of this screen is just that the cop car is getting closer to the intersection, so that explains this, and the robbers are getting further away, so that explains this. Okay, so let's bring that into play. The cruiser's moving at 60 miles per hour, and we've just discussed how the rate of change is negative, knowing that it's getting closer to the intersection. The speed of the car would be like how fast x is changing, which is the rate of change of x with respect to t. And that is specifically the quantity that we're asked to find. Okay? So that leaves me with an unknown value of w, and then we're seeking a value of dx dt. All right, so let's pop over, and I'm just going to grab this screen and paste it over here. If I can do that. Well, let me do that. Nope, nothing like that. Let's see, can I put a handle on these things and group them together really quick? Bam. And now hopefully they'll stay together. Whoops, too much. You can ungroup this guy, and I believe we're good to go. Okay, shrink you down a little bit, and we're all set. Okay, so now we're at the point where we've done some of the modeling, okay, in terms of getting variables set up and understanding the information, translating it into the language of math. Now we're at a point where we can attempt to write an equation that shows the relationship between those variables, and then we can worry about their rates of change. Okay, so what do we know? Well, we're told that it's a right-angled intersection, and we know an awful lot about right triangles. We have a ton of experience with them. And so the distance relationship is simply the Pythagorean equation. Y squared plus x squared should be equal to w squared. And in fact, can I pause for a moment and try to figure out the answer to this little math puzzle here? We have, when this distance is 8/10 and this distance is 6/10, we would like to know the value of this quantity. Okay, so a little sidebar, let me just make some room for this. We know that 6/10 squared, and maybe this will be convenient to do in fractions since decimals can be awkward. 6/10 squared plus 8/10 squared is equal to w squared. What is w? Okay, need to square that. Well, 6/10 squared is 36 hundredths, and 8/10 squared is 64 hundredths. And we're supposed to add those together, which gives 100 hundredths, or 1. So w squared is 1, therefore w is 1. And I'll write it as 1 and no tenths miles. Okay, just to be consistent with the way the information is presented. All right, so we use Pythagoras' equation to determine that the distance between the police car and the car that's speeding away is exactly 1 mile at the moment of interest. Okay, so let me just clean this up and remove that from the work area. Okay, so that little side work was to determine this. We were given these guys right here, and we were able to use math to figure this one out. Okay, so with that, let's go ahead and see if we can come up with an equation to relate the speeds of these cars. Okay, and for that we're going to need to take a derivative. All right, so I'm just going to take each expression here and find the derivative with respect to time. Okay, so I'm just going to bring down the terms in the equation, and then we're going to differentiate with respect to t. To do that, we simply apply the chain rule, which tells us we get 2y times the derivative of what's inside with respect to the t variable, plus 2x times the derivative of what's inside with respect to time, and that should equal 2w times the derivative of what's inside with respect to time. Okay, so by using the chain rule, we're able to get this equation here, which, let me just point out, whereas this equation helps you to figure out what w is if you know x and y, this equation could help you, for example, to figure out what dw is if you know dx and dy. Okay, so it's a relationship between rates of change which is why these are called related rates problems. Okay, and so now I'm at a point where I'm all set to use the information in this table. So maybe I'll just grab that real quick and bring it down to where I can see it. Oh, that didn't work for me. Try again. Can I scoot you down? There we go. Just want to be able to see that table. Splendid. Okay. Alright, so at this point, I'm now going to start substituting the information that I know. Okay. And let's see here. The one that we specifically want to find is dx dt. So we know that that will stay a symbol. Let me just circle that. And everything else should have a value that we can plug in. All right, so just getting set up to do that, I have 2 times the quantity y times the quantity dy dt plus 2 x's times this quantity we want to find, keep it a variable, equals 2 times w times dw dt. Okay, and I'll just use my chart. The value of y at the moment of interest is 6/10. So let's throw that in the equation. The value, the rate of change of y, we were told 60 miles per hour, negative. So we'll throw that in the equation. Value of x at that particular moment is 8/10. This value we don't know, but we'll find out soon. W, we calculated using the Pythagorean equation, is 1 mile. And the distance between them is changing at 20 miles per hour according to the text. Okay? So now we have an equation. We're down to one variable. We just use our algebra skills to solve it. And we can even make use of our calculator as we do this. All right, so using a calculator, I determined that the product of these 3 numbers is -72. And 2 times 8/10 is 1.6 times dx dt. And the product of these 3 numbers is 40. All right, and let's now add 72 to both sides. So we get 1.6 times dx dt equals 40 plus 72. So I think that's 112. And therefore, make some room here. Dx dt should be 112 divided by 1.6. And using a calculator, I'm going to go ahead and compute that. 112 divided by 1.6 is 7.5. 7.5. Okay, time to make sense of it all. We got an answer of 7.5. What does it mean? Well, let's go ahead and recap the information that we were given and the solution that we found. Okay, so let me just hide these out of the way and let's summarize. Okay, so according to the problem, we were told the police cruiser was 6/10 of a mile from the intersection. The speeding car was 8/10 of a mile east of the intersection. We used the Pythagorean theorem to determine that at the moment of interest when the police used the radar. The speeding car was exactly 1 mile away from the police cruiser. Okay, then we were told, and let me just look back at the information really quickly. We were told that this distance was changing at a rate of 20 miles an hour. This cruiser is moving at 60 miles per hour. And our work shows that this car is moving at a rate of 7.5 miles per hour, which seems a little unlikely. Did I make a mistake? Let me go back and see in a second. But this is saying this distance is changing at this rate. This distance is changing at this rate. Okay. And this distance, if you believe our math here, is changing at this rate. Okay, now perhaps that makes sense because they've just turned the corner, and so presumably they've had to slow down, and so now they're just starting out, and maybe they're going pretty slow. But I'll check back and make sure that that answer is correct in a moment. Okay, I've just located a math error, and I think I know how to correct it. It's that I used my calculator wrong and wasn't paying attention. When you divide 1/12 by 1.6, you don't get 7.5, you get 70. So let me just go back and correct that. Now this was unintentional, but I feel it's a valuable lesson because part of the process of solving problems should be checking your answer. And I said, man, my answer suggests that that speeding car is moving too slow. Have I made a mistake? Let me go back and check my work. And in fact, I did make a mistake. I did find it. And now I know that in fact, that car is speeding away at a more realistic 70 miles per hour. Okay, I hope this problem has helped you to understand related rates problems. And let me just go back to this screen and summarize some of the important, just kind of big picture stuff. All right, so two important things happened. Number one, we got the equation that relates the variables. And then number two, we took derivatives and got, I'll just use x prime here, an equation that relates the derivatives. 2y, y prime equals 2w, w prime. Then we just plugged in information and solved for the quantity of interest. Hope this video was helpful to you. We'll see you next time.